All right. Thank you, Darius. Thanks for the invite. All right. Yeah, so I'm the director of machine learning at Motional, and I want to start there because Motional is a new company, so I want to give everyone a short introduction of what Motional is. So Motional is a joint venture between Hyundai and Aptiv. So basically, Hyundai invested about $2 billion or contributed to that, and then Aptiv contributed their self-driving car division. So that was about 700 of full-time employees, including 300 engineers. So this company started, we actually got the name just a few months ago. But we think it has the three ingredients you need to succeed. So it has a long legacy of experienced engineers. It has enough capital to sustain. And we also have the supplier of vehicles through Hyundai. And a little bit about our background. So Aptiv had built up the self-driving car division through an acquisition of two startups, one MIT-based called Autonomy, and that's where I started, and also a CMU based or started from CMU called Automatica. So we were the first company to launch a public AV demo in Singapore back in 2016. We've had a fleet in Boston, and we had a big deployment in Vegas. We actually had a commercial operation with Lyft where people could pull up the Lyft app and actually get a robot taxi within Las Vegas. And then in September last year, we announced this merger with Hyundai. And just briefly, here's our offices, and I want to bring this up in particular because our machine learning office is in right here in Santa Monica in Los Angeles. So we're on the 3rd Street Promenade. We're about 30 people. We're going to be doubling that next year. So if any of this sounds interesting, do reach out, and I have some contacts at the end of the talk. Okay, so what I do want to talk about is I've been working on this now for over 4 years. And I wanted to bring up a couple of things that I think might be interested. So first of all, this is a cartoon of the self-driving car stack, right? So it maps essentially input data in the sense of cameras, LiDARs, and other sensors, along with map data, through a perception system, which is typically some set of detectors, a localization system that feeds into a tracker, and the tracker feeds into a planner, and then there might be a controller here. So this is, of course, not complete. But what I want to focus on this today is the first parts of the data and the detectors. And I'm going to talk about algorithms for how to do that. And then go into some data sets. We share some public data that I want to broadcast and advertise a little bit. And then talk about objective functions. In other words, how do you optimize one of these components so that you're towards the goal of getting a system that works end to end. All right, let's see here. Okay, so what I'm going to focus on specifically here is multimodal object detection. So of course, this can mean a lot of things, but in self-driving cars, the most obvious thing that comes to mind when we talk about multimodal detection is building a neural network that consumes both images and point clouds and outputs a list of 3D boxes, so 3D detections. So of course, an image, we all know what an image is, that's on the right. And then a point cloud is a matrix of XYZ intensity measurements. And then you have endpoints. So that could be 30,000, it could be 100,000 points. So that's sort of the input to the system. And there's a lot of opportunities. It's sort of an obvious argument to be made for fusion here, where they are very complementary. So the strength of the LiDAR is range. It does really well at night. It's sort of natively 3D, whereas the camera is of course has a lot of texture information. It doesn't have any particular problems with black surfaces which the LiDAR suffers from, but it has some other issues. And by the way, I should say, I mean, I know Darius will help moderate, but if you have any questions, just please shout them out. We're a pretty small group here, so I don't mind just pausing and chatting. Okay, but surprisingly, right? So if you look at the KIDA leaderboard, and I'm going to specifically talk about a paper we published this year, And when we started that work, there was still the case when you go to the main leaderboards and the benchmarks, LiDAR-only methods were actually dominating fusion methods, which just seems strange, right? And I actually looked last week, and that's still the case. So does this mean that LiDAR makes vision redundant for 3D object detection? And again, it just can't be the case, right? So if you look at this right-hand side, can anyone tell me what this is, what I'm looking at here? Does anyone know what this is? Yeah,
I see point depth as an answer in the chat.
You see what?
Point depth.
Yeah, it is. Yep, there's points, right? So if I show you the image, you see what it is, right? So these blue points were the pedestrian here, and the black ones were light poles. So just from first principle, it can't be the case that vision doesn't help, right? So why has it been so elusive? Well, one explanation is due to viewpoint. So the world, obviously, that we're interested in is 3D, but the workhorse of spatial deep learning methods is the 2D comm layer. Now, obviously, that might change with the transformers making some very exciting, strides. But still, today, if you're doing spatial reasoning, it's the 2D comm layer. So that means that you have to somehow project your 3D world to a 2D world. And there's two obvious choices. There's the bird's eye view, or it's the front view. And the bird's eye view has been dominant because it's very nice to work with. So Sorry.
I don't know if it was just me, but the sound was really bad for a moment.
Oh, really?
Oh, now it's okay.
Okay, all right. Okay, cool. So in the bird's eye view, you have a lack of scale ambiguity. So, like if you look in this front view, this vehicle here is, say, 200 by 200 pixels, but the vehicle in the back is maybe 30 by 30, right? So they're physically the same size in 3D, but the projection is different size. You don't have that problem in the bird's eye view. All the vehicles here will be the same size in the canvas, which is really nice because, as we know, 2D convolutions are actually not scale invariant. You can learn a redundant representation that it can handle scale, but they're fundamentally not scale invariant. You also have much fewer occlusions. Again, if you look at this bird's eye view compared to this front view here. However, it's hard to project images to bird's eye view, right? So LiDAR, it doesn't matter. You can project them either way. But for images, there's obviously a very natural representation in the front view. And then to go to bird's eye view, you have to start doing structure for motion, dense depth, or any other kind of processing to get there. So what do we do, right? So I'm going to discuss 5 different flavors or families of methods in the literature that attempts this, and discuss some of the pros and cons, and then go into what we ended up doing. Everything clear so far? Yeah, nice. There's only two person with video, but I appreciate the head nodding. All right, so front view fusion, right? So this is a nice idea. Thank you. Where because the image is naturally front view, why not project the image or the LiDAR into the front view? Now everything is front view, and it's sort of the same representation. Well, and here my problem is something called depth blurring. So if you have the depth map here, and this is from a paper called pseudo LiDAR. So you take the depth here, and you see where these points map into the bird's eye view. Now, if you run convolutions on the depth map, of course, you're going to start blurring them, right? So the objects that are quite crisp here becomes really blurry in the bird's eye view. So, and that's, of course, an issue with just the fundamental design of the 2D comm layers. You also have all this scale on occlusion problems that you see in the front view. And it's also harder to incorporate auxiliary inputs like map layers. So this is a neat idea. There is some interesting work in this space, but it tends to not do as well. This is certainly the outlier in the field to work in the front view. Another thing you can do, there's a question from Benjamin.
Hey, can you hear me?
Yes, yeah.
My camera, sorry, it's not plugged in.
Oh, that's all right.
Yeah. So this all makes sense if one thinks of the bird's eye view, right? But I mean, in principle, for driving purposes, it would seem that, I mean, we humans see the objects that are closer with more detail than the objects that are further away. And for driving purposes, the objects that are closer are more important right away for driving decisions than the objects that are further away. So while I understand that a bird's eye view is conceptually simple, it's not really clear to me why, for the purpose of autonomous driving, it's necessarily bad to have all these things that you mentioned before, that objects that are closer have more detail and objects that are further away are more blurred and so on. So I mean, other than conceptual simplicity, what's sort of the fundamental point for the bird's eye view? Or what's the fundamental disadvantage of the things that you mentioned?
Well, I mean, ultimately, if you have a lower quality detector, so if you work in the front view, the scale ambiguity means that the network needs to learn more, right? It needs to handle multiple scales. And that makes the network less discriminative, basically.
Well, if one were to design something that doesn't rely on the bird's eye view at all, but is sort of essentially a route planner that automatically is built on the fact that nearby objects are sort of bigger and more detailed and further objects are further away, one wouldn't need that. I mean, that's what we humans do, right? Or do we humans have so much context that we put everything into the bird's eye view automatically?
Yeah, I mean, I think that... I think you bring up a good point. And I mean, to be clear, even in the bird's eye view, you'll have more detail closer by, right? Because the point cloud will be denser point by. So you tend to always do better close to the vehicle, which is exactly what you want. But
I'm wondering if that's just why we're thinking in bird's eye view, right? When we're designing these systems. But when we're driving, we're not doing that, right? Or I don't know, or maybe we are, right? But I'm just wondering. It's sort of, it sounds very convincing in the beginning, but
yeah, I mean, the internal representation of the human brain, I think, is, I don't know what that is. I guess I'm just making an empirical argument. I mean, all of this, right, is, unfortunately, we're doing applied machine learning. So a lot of this is trying to attach intuition to empirical results and try to tease out what ends up working. Mm-hmm. So, no, but it's a point well taken. And maybe, in the third part of the talk, I'm going to get into some of the stuff you mentioned, that we need to be careful what we're optimizing for, right? So if we're optimizing for object detection everywhere, that might not matter for the final performance. But if you look at typically how these benchmarks are evaluated and the detector level are evaluated, you tend to look at things like mean average precision, which counts objects equally.
Okay, great. Thank you.
Right. So another way to do this is to do object-centric fusion. So this was basically the first family of methods. This is the first thing that came to mind, essentially. So what you do is you run, if you guys are familiar with something called faster RCNN from the computer vision literature, we have a two-stage detection system. So you run, all the pipelines run separately. You do object proposals in 3D from everywhere. And then you take all those proposals and you accumulate information across all the different viewpoints into those proposals. So conceptually, I think it's a very nice idea. End of the day, it ends up being slow and cumbersome. And it just doesn't do that well. I think two-stage methods in general are difficult to optimize, and especially if you want them to run real time. But I think that's definitely one family of methods. Another one is to say, okay, we want to do kind of single-shot learning, like a single-stage detector. So there's this idea of continuous feature fusion, where you try and at every step, so you still run two different backbones. You run the LiDAR backbone in the bird's eye view, and you run the image backbone in the front view. And you try at every feature stripe, fuse information across, okay? So there's one prominent paper called Confuse from Uber that attempts to do this. There's several other works. There's one from Berkeley as well in this space. And fundamentally, the problem is something called feature blurring that I'll explain in the next slide. And let me try and walk through this. So at the raw point cloud level, right? So you have, let's say I take all the point clouds in a particular ground plane bin. So I take all the points that say, fall onto this light pole here. Okay, and let's say that this LiDAR point here maps to the bottom of the light pole, and this up here maps to the top, something like that. And of course, because the LiDAR are X, Y, Z, you know exactly where you can just project them into the image, and you know exactly the relationship between the image and the LiDAR, right? However, the problem is once you start running a convolutional backbone in the bird's eye view, you have no interpretability anymore in the. This is no longer a Z. This is now channels in your feature space. So you don't know which of these channels, where they map, into this epipolar line in the image. So if you want to start fusing across, you end up blurring the image features and the bird's eye view features together. So I think that's the fundamental problem with these sort of feature fusion methods. All right. So another thing you can do is say, okay, well, we think bird's eye view. You argue with Benjamin, and you say, okay, I still think bird's eye view is the best. Let me try and put the images in the bird's eye view, right? So this family of method comes out of the literature where people try to use only images. It turns out even if you use only images, one of the best things you can do is create a fake point cloud and then do reasoning in the bird's eye view. So
I have a question in the chat. So what are the assumptions you make about the density of the LiDAR?
So it depends on the manufacturer. So the Kitty benchmark is 60,000 or so points. In the nuScenes benchmark, it's about 30,000 points. So it's going to be a lot sparser than a lot fewer data points than the image.
And there's another one. Why is feature blurring terribly bad? Humans blur features all the time. Gestalt comes to mind.
Again, I don't I don't know enough about the humans, like the internal representation of the brain to discuss that. So I'll defer to someone who knows that better. So one thing you can do here is once you have you can kind of use dense depth or structure promotion. Now you can project the image into the bird's eye view. You can overlay it with the LiDAR points, and you can do reasoning there. And this is an appealing strategy. The only issue here is that you add an expensive computational step where you need to do dense depth, and you need to do this projection of the image features. And then the final family that I want to mention is something I call it detection seeding. So the most prominent example is a paper called Frustrum PointNet, where you try and do things on the 2D first, like here you do a 2D detection, and then you look at the frustrum that extends from that 2D detection, and you use that to constrain the detection problem in the point cloud. So you say, okay, I know there's a vehicle somewhere in this cone or this frustrum, and it's a little bit easier to find where that is. And there's some other more recent papers that kind of follow this line of reasoning. And obviously, the fundamental problem is that it's an upper bound on recall. And again, it tends to become expensive. None of these methods are what I would consider real time. Okay, so finally, let me get to the paper we has the method we proposed, and this is presented at CPPR this year. So we call it point painting, and it's a sequential fusion method for 3D object detection. And what I'll show you is that it actually improves 3D detections across classes, across data sets, and across the underlying LiDAR detection methods. And the method is very simple. The actual algorithm is given in the top right, but I'll explain it with these images instead. So you take an image, you run a semantic segmentation in the image plane, and here, of course, you can reuse anything you're already running on the car or any state-of-the-art segmentation method. Now you take your point cloud, and what you do is you project them into the point cloud. You quote unquote paint them, or you attach the semantic output of the image network, but then critically you go back where you started. So you go back into the point cloud. So you get this painted point cloud or augmented point cloud. So now you have, instead of just XYZ intensity, you have XYZ intensity plus the probability of being that the image, thinks that this point projects into a car or a pedestrian or a bike. And once you're here, you can now run any LiDAR detector. So point RCNN is one very popular one. Point pillar is another one that we developed. You get into, you can do your 3D detection. So I want to say there's an obvious drawback here, right? Is that this is actually not optimized end to end. So we are kind of optimizing this separately from this. And there's, if you put on your engineering hat, there's actually some nice advantages to that. Of course, if you put on your scientist hat, I think it's unsatisfactory. And it does address all these shortcomings. So it doesn't add any restrictions on the 3D detection architecture. There is no feature of depth blurring. It doesn't require a pseudo point cloud to be computed, and it also doesn't limit the recall. So we haven't restricted the search space, we've simply augmented it. And we show that, so here we try and paint 3 different methods from the literature: point pillars, voxelnet, and point RCNN. And in all cases, there is basically 1 or 2 outlier or exceptions. But other than that, painting improves across methods and across classes, which I think is really exciting. We also show that at the time we submitted this was actually enough to establish a new state-of-the-art result on Kitty. I don't know how many of you guys have worked on the Kitty leaderboard. It's a little bit messy, to be honest. But among the published methods on Kitty, when this was submitted, it was state-of-the-art. And we also show on the nuScenes data set that I'll talk a little bit about next is it also worked, right? So, and that was sort of the criteria for me. I wanted a fusion method that actually generalized across data sets, classes, and underlying methods. It shouldn't be so sensitive that it only works for a particular architecture.
There's another question.
Yeah, please.
The semantic segmentation does not take depth into account. And this was also something I wanted to ask. Usually depth is a lot stronger in segmentation queue than appearance. So if you have many objects in front of each other, that allows you to separate them more easily than doing it in appearance.
Yeah, I mean, so again, once it's hard to see on this image, but this painted point cloud is still XYZ and intensity and the semantics. So these are still, a lot of the detectors, like I said, pretty much all of them operate in the bird's eye view. So you take this point cloud and you still look in the bird's eye view. So you have all the depth information already available from the LiDAR. And sort of the argument we're making is that LiDAR is, depth is the bread and butter of LiDAR. Like it does depth estimation really, really well. So let's just add what we get from the core component from images, which is the semantics. Like images are really good at saying what things are, but they are worse at saying where they are, right? So we're just saying, what are they? And then we let the LiDAR representation figure out where they are.
Maybe one more, and then
please.
How does accuracy of semantic segmentation affect 3D detection quality? So maybe.
Right, that was my next slide. Thank you for that question. And of course, there is. We showed in ablation that there is a relationship here. So, as you would expect, the better, the more the merrier, and the better you do. In practice, we've tried a few different methods, and we've always seen a positive improvement. And again, this depends. Like if you put on your science or engineering hat, if I put on my engineering hat, this is really nice to see, right? Because now I can have a team optimizing the image network, and all those benefits just carry over to the 3D detector. Whereas, so again, I think there's pros and cons to this, but it does affect it, and there is a positive correlation. Another thing we showed here is in the paper is that you can actually, if you think of this as a real-time system, which is obviously what we're striving for, if you have to run a neural network on the image first, and then take the output and run the neural network on the LiDAR, if you're matching images in point cloud as they come in, you actually have to wait until the image is processed until you can run the the last stage, right? But so what we try to do is just match consecutive. So you match the LiDAR with the previous image. And we showed that it actually works really well also. So we don't really see any drop in performance. And that means that we actually don't incur any latency of this.
There's also a question from Benjamin. How about matching errors, raindrops on camera, and so on?
Yeah. What about it?
Maybe I unmute you. Let's see if I can find them.
Well, even before the raindrop, my question is just being completely ignorant about these things. I mean, you have a camera and you have a LiDAR, right? And you want to identify which pixel of the LiDAR corresponds, or which point on the LiDAR data corresponds to which pixel in the image. I mean, that in itself is non-trivial, right? They're not exactly identical, right? You need to know the transformation between them. Is that correct?
That's correct. That's correct. I mean,
that by itself probably is prone to a little bit of error, right? Like shaking of the components and so on. I mean, we're talking about very detailed pixels on these cameras. Then now you have, let's say, rain or something like that, right? That distorts it. That distortion might be okay if you only rely on the camera data, because it still results in an error bar of only 10 centimeters in the real world or something. But when you want to fuse them now, this might cause real problems.
Yeah, you're right. I mean, first of all, the electrical engineering that went into creating the next section I'll talk about, nuScenes, is astounding, right? I mean, the LiDAR spins at 20 hertz, and we're triggering the cameras exactly when the point cloud sweeps over the center of the image. We have a very, very accurate localization system, so you have a generalized transform to go between the coordinate systems. So I agree that is a marvel of engineering just to get that right. And then, of course, you're right. I mean, any issues like any droplets will make any fusion methods more complicated, right? Whether it's tight fusion or whether it's downstream fusion, or whether you fuse it in the tracker stage. So, yeah.
Right, but what is it from a real, honest, practical perspective, right? Is it that these are engineering challenges that can be addressed, or this is a real problem going forward with these fusion methods? Because there will always be, like when a system is a month old, the metal deforms a little bit, the camera is slightly off center or something. I mean,
yeah. So that comes back to the business model. I mean, we are planning to deploy a fleet of taxi services, autonomous taxis, right? So we're not Tesla that try to sell a vehicle and then kind of walk away from it. So our vehicles will go back to the garage every night. They will be calibrated. I don't know if it's daily, but at least I imagine it's daily or at least weekly. The sensors will have, air that cleans out droplets from them. And we have detection systems solely to detect noise on the sensors so that we can pull that vehicle out of service and clean it. So, I mean, this is a great, I mean, I can talk for hours about that. That's a whole,
maybe we take it offline later.
No, great, thank you.
Yeah, 11 minutes and 2 parts. It may be challenging.
We just have 10 minutes left. Okay. Well, this was the most interesting part, I think. Well, I don't know. I think the third part is the best. I'll save the best for last. So the public data sets, and I just want to put up this slide to say about non-public data sets is that actually building these data sets is the hardest and most nerve-wracking and critical part of building these systems, right? Because it takes so long to accumulate the data you need. So you're making decisions about taxonomy, annotation instructions, corner case, design choices that comes to bite you like a year later, right? That's opposed to if you find a new algorithm, in the literature, it takes you a week to implement it, and you try it and see if it works. But building up these data sets is very, very difficult. I'm not going to talk about that today. I just wanted to flag for that and say that you're in luck because we've done all that hard work, and this is the data set that we've shared. So nuScenes was published or announced. The full release was in 2019 in March. So we've released 1,020 scenes from our data. These are actual, AV quality data. So you have 6 cameras, you have a 360-degree LiDAR, you have a bunch of radars, and you have high-definition maps. This is fully annotated in 3D, and it's freely available for research. So again, this has been very well received. I think it's over 300 citations already, which is pretty crazy considering how short time it's been out. And the reason I took this initiative was that when I started my job 4 years ago, there was only one data set available, and it was Kitty. And Kitty is, of course, amazing for what it was, but it was just getting very, very small. And you can see that on the leaderboard. If you try to submit, it's way too small to regularize the kind of state-of-the-art benchmark methods today.
Don't you have a privacy problem with the dataset? Because what most people don't know, that if you use Kitty as a company, you may get yourself already into trouble because of the privacy rules, at least in Europe.
So we blurred faces and license plates in nuScenes, so we think we're good to go there.
Mm-hmm.
And then there's been a lot of companies that follow suit. So Argo released Argoverse, Waymo released Waymo, Open Dataset, Lyft released their version, and so on and so forth. So yeah, it's been, nowadays there's a plethora of data, maybe 7 or 10 public data sets. And this is just to show that, the amount of training data, if you look at the volumes available in Kitty versus in nuScenes, you see that the ordering among the methods could actually change. And of course, if I had 10 times as much data, it could change again. But I think, at least from the studies we run, it's more stable when you start approaching the volumes of nuScenes. And I'll skip 1 or 2 slides here just for interest of time. We did release a new data set called New Images, which this was just last month. So it's 100,000 images. And this was asked from request from users. So this is a pure image level data set, but it has all the variety and the details of nuScenes. And we also released LiDAR segmentation annotations for nuScenes. And I'm really excited about this. So we took all 40,000 keyframes and we did semantic segmentation annotation of all of this. So I just want to show you what that looks like. So what you're seeing here is the LiDAR projected back into the image. And it's a little bit, I don't know why it's so, this is just 2 Hertz because it's only the keyframes, but you're seeing an amazing level of detail, right? So the turquoise is the free space. You have different shades of green for different types of vegetation. You have vehicles, vulnerable road users, obstacles, and so on. This looks blurry on my screen. I can only imagine it looks terrible over over through Zoom. It's okay. If you go to nuScenes, you can there, we have posted tons of these videos. You can play around with the data. So I have 5 minutes left?
Yeah, 6.
6, excellent.
I guess a little bit more because we had questions already during the talk.
Okay, great. So let's make it 8. So objective function. So this is something that's near and dear to my heart. So what happens when you sit, like I said, we've done a lot of work in this part of the graph. So image detectors and LiDAR detectors and fusion detectors. But of course, as I mentioned earlier, we don't really care about, and the way you typically measure detectors is stuff like mean average precision, maybe precision at certain distances or certain classes. You can define all these different ways to measure it. But in the end of the day, it doesn't matter, right? What matters is how well does the planner do, right? Or the controller, like the final output of the system. So there's two challenges here. One is how do you accurately measure the output of an AV? And one is how do you then propagate that to the subcomponents? And I'm going to talk about the first part today. And let me just skip this because in the interest of time. Okay, so this is this figure on the right comes from a white paper from my colleagues called Rulebooks. And what they're trying to do here is address the fundamental problem of how do you score an AV, right? So if you take a W here, which is a scenario meaning a map, other agents, and the trajectory you choose to pursue yourself, you need a function that maps that to a score, right? The scoring function. You need it for two reasons, and probably more, but two fundamental reasons. One is to optimize the stack, right? You need an objective function for your optimization problem. And second of all, you need it for retrospective. Like if something happens, an accident occurs, you want to understand why the decision was made to act that way. And it's what I come to realize, and this is probably not obvious for people outside the space, is that it's not obvious what F should look like, right? So there's legal, ethics, culture, all impose constraints, and they're often conflicting. So you could have laws that literally conflict with each other. So what the rulebook's idea was to say, you take each of these rules, we write down explicitly in a formal language how much you violate each of the rules. And again, they could be legal, ethical, or cultural. And then you impose a partial ordering across the rules. So for example, here, so you put safety of humans first, safety of property, and then kind of trickle down like this. Now, here's an example, and I'll skip this in the interest of time, but just to show that there is a lot of work put into making these really precise. But how do you combine the rules, right? So I was talking to Emilio, which is our co-founder and CSO, about this. Like, how do we, on the end of the day, what matters, right? If we have an accident, we go into court, what is the lawyer going to say, right? And they're going to say, an AV needs to do what a reasonable person should do. And the reasonable person here is a legal construct that's used in situations where in gray zones, in the legal gray zone, where you go into court and you say, well, there's conflicting laws around this. Like, what would a reasonable person do if they're in this situation? So that's, so that's one way to approach this problem. So with that in mind, I started a project that I called the Reasonable Crowd. And what we said, let's try and crowdsource it. So let's try and show humans options, like same scenarios, the same map, same agents, and you say which one would you do? Like what do you think a reasonable driver would do in this situation? And of course, you can generate millions of these, and you can crowdsource this. You can get a lot of data. So basically what I'm doing here is, instead of saying f of w to score a scenario, I break that down into two functions. One is f of rules, which maps the whole scenario into a vector embedding of rules that is hand engineered and interpretable. And then we have this f crowd that we learn from data. And if you constrain f crowd to be, say, a linear function, or a very simple, maybe say a decision tree, you actually achieve some level of interpretability on the output, which I think is nice. So this is in submission. I just want to share a couple of very preliminary results. So here is an example of what this looks like. Let's see if I can do this. Again, maybe this is going to be too blurry for you guys to see. Let's see. Yeah, I think it might be. Yeah, so here, for example, so you're driving along the road here. There is a person jogging along the side. And you're going to see in one case, on the right side, the vehicle will start giving a really wide berth to the pedestrian, whereas in the other one, they're following the lane, right? So here on the left side, they're violating the kind of, it's not an actual rule, like a law, but you should give a certain, maybe it is actually, I shouldn't say, I'm not sure. But, they're violating the constraints of giving people enough space on the road. On the other side, they're violating the constraint of staying in the lane, right? And you can look at multiple of this. I think, let me just, again, in the interest of time, I'll skip that, but you get the idea. So there's several situations like this with different trade-offs. Right? And a couple of data analysis points here. So worker agreement is surprisingly large. So we can get, some of these are very, very similar. But if you look at agreement with the majority vote, it's in the 80s and 90s. And just putting a linear model on top of this, we get something that would be like the second worst worker. So kind of not as good as the best humans, but in the ballpark. And again, these are preliminary results, and this this could be due to a limited rule embedding, or it could be limited capacity on the machine learning model.
There is a question in the chat. How about AV Turing test? Can humans determine if a human or computer drives the car?
I don't know. You mean instead of asking these comparisons?
Yeah, I guess.
I think that's a nice idea. That's a nice idea. I like this comparison because it just lends itself well to posing an optimization problem later. Yeah, and this is an example. So I wanted to show you this one. So you can actually, once you train these things, you can now look at the weights that the linear model assigned to the different rules. And you can now start saying, well, the collision is the most important one. Pedestrian clearance is important. Park car, stay in the driver lane, and so on. Drive smoothly is the least important here. So this is sort of what you would expect. And maybe you can come up with this by yourself. But I think this offers a complementary approach to this. Yeah. And again, ongoing work is to, now we know how the system should work. Now let's figure out how the subsystem should work. And I'm not going to talk about that, but if you are interested in it, do reach out, because we are literally staffing up a team focused on around these questions this year. All right, so that's it. Thank you again to co-authors and colleagues. If you are interested in a position, here are some links for you. And if you're interested in get started working on this field, you can check out nuScenes. Thank you.